Hello and welcome back. We have been discussing the concepts in Chapter 16 and focusing our attention on the mass spring system and the pendulum system and introducing some quantities that are characteristics of waves. So now we're going to discuss some additional quantities that all waves have in common. And so up here at the top, we are just defining to begin with, what is a wave? A wave is a disturbance that transfers energy from one place to another. With the exception of electromagnetic waves get the symbol EM, waves require an external medium to transport the energy. So in space, there is no external medium, so the only waves that can travel in space are going to be the electromagnetic waves, the ones that don't require an external medium to travel. So I've drawn waves here, two different diagrams of a wave. One is a wave in time. What do I mean by that? Well, I've got the amplitude of the wave on the vertical, and I've got time on the horizontal. This other diagram is a diagram of the wave in space. So I've got the amplitude on the vertical, but on the horizontal instead, I have a spatial coordinate, x in this case. I could have chosen y or any other symbol, but x, and of course units of meters. So I should change these units. This is units of seconds. So we've got a wave in time and a wave in space. Let's focus in here on the wave in time. Notice that there's some maximum amplitude that the wave is swinging through. So it's swinging through some maximum and some minimum. In addition, this wave is periodic. It's repeating itself. So notice that it goes through these highs. These highs are called crests. And then through these lows, and these lows are called troughs. So you see here the wave comes up through a crest, comes moves through zero amplitude, and then back down to the trough. I've drawn a dashed line as it transitions from the crest to the trough, going through zero. And notice I've done the same thing for the very next place that happens. This is a rise. It's moving from a trough to a crest. So that's not the same thing as moving from a crest to a trough. So moving from a crest to a trough here, I've drawn another dashed line. This is a full cycle in time. A full cycle in time gets the name period and the symbol t, as we've seen earlier. And recall that period is 1 on frequency. So this is representing a period in time, a graph in time. Now come over to the wave in space. So again, we have the amplitude on the vertical, and this would correspond to the maximum amplitude here. And notice again, I've drawn from crest to trough as it passes through zero as my first dashed line here. And then finding the very next place, it goes from a crest to a trough and passes through zero, boom, right here, another dashed line. So this is a full cycle in space. So this is a full cycle in time. This is a full cycle in space. The full cycle in space is known as the wavelength of the wave, and the wavelength of the wave gets the symbol lambda. This is a letter from the Greek alphabet, lambda. So this distance is going to be in units of meters, and it is the distance the wave travels before it begins repeating itself. T, the period in time, is the time it takes the wave to travel before it begins to repeat itself. All right, so the speed of the wave. How fast does a wave travel? Well, the speed of the wave is given by the distance it takes to travel a full cycle divided by the time it takes to travel that full cycle. So the wavelength over the period. Notice that I can take 1 on the period and redefine it as frequency so that I can write the wave speed as the wavelength times the frequency. These are sufficient, either one of them that you want to use. To give you an idea of some wave speeds, sound in air, sound waves that are traveling through air, our atmosphere, dry air, sea level, the wave speed is about 340 meters per second. So in 1 second, dry air, sea level, a sound wave will travel approximately 340 meters. Juxtapose that with the electromagnetic wave that is traveling in vacuum. For example, the waves that carry energy from the sun to planet Earth. Those are electromagnetic waves, some of which, and most actually, that we can see with these detectors in our eyes, called the light part of the electromagnetic spectrum. Those waves travel in vacuum at 3 times 10 to the 8th meters per second. Much, much, much faster than sound waves travel. And in fact, sound waves can't travel in space because space does not have a medium to transport sound waves. The only waves that can travel in space are electromagnetic or EM waves. The last thing I want to talk about in this video is wave intensity. Wave intensity gets the symbol I, and it's the power per unit area delivered at some point. Power, recall, is energy per unit time. So this is energy per unit time per unit area. And so the units that we're going to have for intensity are going to be joules per second per meter squared. And remember, a joule per second is also a watt. So as an example, for the sun's electromagnetic waves that strike the Earth's surface at sea level, the maximum intensity, and it's going to, of course, correspond to how much cloud cover is in the atmosphere above that point, and also what the humidity level is, and also what the angle that the sun's rays are striking the surface at. All of those are factors in determining what the intensity is at the surface for the sun's rays. So we're going to say that this is the maximum possible intensity. 1,000 watts per meter squared. So that means there's 1,000 joules per second per meter squared being delivered by the sun at sea level when we have totally normal incidence. In other words, the sun's rays are striking the Earth's surface perpendicular to the surface with no cloud cover, maximum intensity. So we've got a few more characteristics to talk about as far as waves are concerned, and we will discuss those in the next video. So we'll see you then. Thank you.